So good afternoon, everyone, and welcome to the Altair TechBrew series. Just a quick check that Swapnil, can you see my screen and hear my voice?
Yes.
Okay, great. Yeah. So from past couple of weeks under this TechView series session, we are bringing some of the interesting topic, which are like the short topic, which we are trying to cover up in 30 minutes, giving a glimpse of some of the very interesting and latest features in Altair solutions. So today's topic is analyzing structural behavior under electrical loading in Optistruct. Okay. So with that, I welcome you all. Yeah. Okay. So Optistruct has a broad spectrum of solution, which I believe many of you are using Optistruct for one or the other cases mentioned here, starting from the regular strength and durability to NVH, and of late, like Optistruct has a new capability. Optistruct has added new capability into simulating the electrical load and thereby analyzing the structural behavior by understanding the heat impact what this electrical loading has on those structures. And now Optistruct supports even explicit simulations as well. So in this TechView series, there is down the line also there are sessions on fatigue, there are sessions on explicit. So I encourage you to join those sessions as well. Today the topic is dedicatedly on electrical. Okay, so electrical loading. So here, if I take the scenario in our machines and equipment, like there will be cycles where the current is passing either in a linear steady state way, or there are possibilities where there is a start, stop, and accelerate, those kind of cycles. Normally, like these driving cycles, from the testing terms, either it will be so following some of the like new European forms or there are some world standards for these cycles, the way it has to be tested. That is from the testing point of view. But whenever we go through these type of events, there is a change there is a contents change in the current, or there can be cases where it is steady also. So here the idea is Optistruct already had a thermomechanical multiphysics capability where with a steady state, with transient, with nonlinear. So we were doing the thermomechanical simulation. But like now the extension is, so from the electrical loading, which can be like voltage or current. So from that, we are trying to understand what is the rise in the temperature, and those temperature we are bringing onto the structure, and we are simulating the structural performance. Okay, so in that way, it is now it is the electrothermal mechanical simulation. So where we were doing thermomechanical already, now we are going one downstream and getting that load more realistically. Okay, so this is the extension now. So in that way, yeah, in this, I believe like, yeah, including me, most of you are mechanical engineers, and we have been dealing with the stress strain altogether, and our force and other things. So today, so let's see some of the new entities uh, for doing our simulations. Okay, so from the FE finite element point of view, like here we are trying to solve equations which are basically having electrical conduction matrix and electrical potential and current. Okay, in simple terms, so these are the entities by which we are trying to solve the equations. And this capability of electrical analysis is available from version 21.2 onwards. Okay. And also, as it is a short session, uh, uh, please feel free to post your questions in the chat window. In the panel, I have my colleagues Vinay and Rajendra, so they will try to help you with the answers. At the end of the session, also, if there are some questions which are not answered, then we'll definitely reach you out with the answers. Okay, so please feel free to post your questions during the session. Okay, and as it is a new analysis, what we are adding into the Optistruct, of course, it requires some of the new cards. So here I'm exposing those cards in a different categories. Like now, here the analysis type is like now this analysis electrical, and also as this electrical effect has to be accounted in the thermal and other subsequent cases. So that reference we are bringing it to the joule. Okay, so there is again a new card which we'll be using it as a reference. So I'll be taking one case down the line here, so where I can go more deeper on how we reference this, how we link this on those aspects. And from the output request point of view, so these are the new electrical output in terms of the old voltage, heat, and there are output on like current capacity and resistivity, those sort of outputs. Okay, so those are available, conductivity, resistivity. So all these output we will see when we solve the simulation. And like the O load is a standard thing which we put to understand the applied load. So here the applied load may be current. So here we'll still use O load to understand those applied entities. So these are some of the output requests. Now, as far as the loads and boundary condition it goes, it is still again SPC here. And we have for the SPC, the way we define it, that will get varied, but still for the voltage, which is potential, electrical potential, we'll use SPC, which is voltage. And for current, we have a new loading card current, and loading can be also in terms of current density. For that, there are new cards. And here, from the material point of view, for the electrical, one of the main aspect is like the resistivity which is offered by the material. Okay, so for that, there are new materials, MAT1 EC and MAT2 EC. One is isotropic, another is anisotropic. In the anisotropic, you can define this resistivity in all three different directions. Okay, so this is the resistivity offered by the material. So in that way, if the resistivity is higher, so in that way, the temperature rise will be higher. Okay, and also this resistivity can get affected with the rise in temperature. So that's why, like as we have many of the temperature dependent material, MAT TT, so we have MAT TT again 1 EC and MAT TT 2 EC. So in that way, temperature, these materials can become temperature dependent material also, where you can have a material curve defined with respect to temperature and change in the resistivity. Okay? So we'll see that again. And we have again this simulation also work with contact. So again, with the change in the contact clearance, with the change in the contact pressure, there is a possibility of conductance. There is a possibility of change in the conductance. Okay? So we'll see that as we go along. So these are some of the new cards from the loading and from the material point of view. So this is a good slide which I like. Here we are trying to somehow relate between our electrical, thermal, and structural simulation. So in terms of like what all the equal entities, I will not say that are equal entities, or maybe the entities which are of interest in that particular kind of simulation. Like when you're doing a electrical analysis, your result interest may be potential and electrical field, and in thermal temperature, of course, and in our regular structural it is stress, strain, displacement, those sort of things. Okay, so this I think table gives some idea regarding in each these type of simulation, uh, what are the loads or what are the materials and what are the output. Okay, of course it is not a exhaustive list, but just to give you an idea on the entities between different analysis. Okay, so with that, now I'm going into the analysis case as such, like how to define this case, and there are quite a lot of variety in this. So to give an understanding of that, so broadly, these electrical cases can be classified into two categories. One is steady state electric conduction. In this, what is assumed is either current or enforced voltage. They are constant. They are time independent, and they are constant. Okay, so where you have one value as an input, what you're going to provide. So in that way, it can be, in our terms, it can be told, it can be said as the linear cases in terms of the loading what we are bringing. And we have this multi-steady electric conduction in which these entities can be given as a transient signal. That's why you're seeing it, the very familiar deload cards, and followed with in the bulk data will be having T-load entries. And there we can call this joule and current as a transient data. Okay. So in that way, at this stage, two classifications are, like there is one which is steady and one which is transient. Okay, so from the current point of view, from the loading point of view. Now, if I go little further on coupling, okay, like now here the main idea is how we couple the simulation with the thermal and how we couple the simulation with the structure down the line. Okay, that is the main focus. So in this coupling, there are two ways. Let's see that one by one. So the first one is a very simple one where like I'm performing electrical simulation and I'm understanding uh, I'm understanding the temperature rise because of those electrical loading, and I'm performing my thermal simulation. Okay, so here I'm not at going to structural part, which is just a follow up of this, but here I'm just showing the flow between electrical and uh, thermal simulation. Okay, so you can see that I have a electrical simulation. Here again, SPC maybe like my voltage and load will be my current, those sort of things, and I perform that, and that I'm referring here as joule. Okay, so where this is a linking, which is creating a linking between my electrical and thermal simulation. Okay, so this is one way. And similarly, like in the transient way, again my flow is same, but like now I have a deload. So in the deload, as I mentioned, you have this joule reference, as we used to have our displacement acceleration as a transient signal. Like now there is joule and there are table which will have the transient information. Okay, so in that way, here we are just uh, from the electrical, it is thermal. Okay, so this is one-way coupling. Okay, like now the extension, like now let's say I mentioned uh, like in the electrical there is a possibility we saw a material where even in the electrical we can have a temperature dependent material. Okay, so I'll perform electrical simulation and I'll understand the temperature, and we are doing a thermal simulation, and from that I have a change in the temperature of the structure. So that has a possible impact on changing the electric characteristic of the entire structure. Okay, so as the temperature rises in the structure, there is a possibility that there is a change in the resistance from the structure. So the way current will flow in that structure may vary. Okay, so here we are talking about a two-way coupling. So wherein, so from the electrical, I am finding the thermal behavior, and again when there are changes in the structure here, so it can understand what are the changes in the temperature, and for that what is the change in the resistivity, and it can perform again electrical simulation. Okay, so this is a two-way coupling. Okay. So today the case what I'll be showing in the setup, that is a two-way coupling case with the steady state. So where we will see all these things, all the further information on these things. Again, in similar lines. So here again, not much change. Only the loading is transient here. Otherwise, all the other physics remain same. Okay. So this is yeah, the two things what we are talking. Like one is one-way coupling and two-way coupling. And in my case, also I will take it further to the structure. Ultimately, we want to see the stress and strain and structural deformation. Okay. So in this, we are only talking about electrical and thermal. But later in my example, I'll be getting into our regular structural case also, followed with this. Okay, so this is the overall scheme of simulation, how we want to perform. So with that, let me quickly move to model here. Okay. So yeah, here mainly I want to explain you the setup of this entire model. So I have a busbar model here. In terms of mesh here, it is a completely connected assembly. It is okay. So there are some connectors, electrical entities, uh, regular busbar kind of assembly, but it is a connected mesh. Okay. So why I'm stressing on that is there is also a possibility of adding the contact, which is not there in this model. This is a connected model. It is okay. So that is one. And now to start with, yeah, on the material side. So if you see, there are two kind of material. One is electrical conductive material, which is a pure copper, and I have a dielectric material also, okay, which is non-conductive material. Okay, so if I just try to isolate, yeah. So this entire component is conductive material, and I have these parts which are dielectric, okay, non-conductive. That is one. Now let's see like what all the data this material has. So yeah, now I'm getting into the pure copper material. Yeah, so in this one, I have the regular our MAT1 property also, because downstream I want to perform my regular structural simulation, so I need this one. Okay, so I have my regular MAT1 data, and in this one the important information is yeah, I have expansion, coefficient of thermal expansion. I have it, and I have material related information on the thermal conductivity. Okay, and here importantly I have the information of conductivity versus temperature information, which is coming from a curve. Okay, so this is yeah, so this is a curve between temperature and conductivity. Okay, so you can see that I have temperature and conductivity, change in the conductivity, that information in the material. Okay, let me go back to material. Yeah, so information here, it is complete from the structural side, it is complete from the thermal side. Now the new information is from the electrical side. Okay, so that is where you're seeing this new material MAT EC. Okay, so in this one, again, like this material also, like what we have defined here, it is a temperature dependent electrically conductive material. But in this version of Hypermesh, it is not writing MAT TT EC1 material. Okay, so which is coming under my unsupported card, but that's a very simple card. So let me show it to you. Okay, yeah. So this is the MAT TT1 EC. So this is my temperature dependent electrical conductive material. It is having ID 19 and it is calling one table 103. Okay. So again, if I see what is that 103, okay. So I have curves here and it is table G. This is 103. So if I say this, yeah. So this is again temperature and resistivity. Okay, that value, it is means in terms of unit system, it is quite small, e to the power of -8. That's why we're seeing 0 here, but otherwise you can see in the curve, it has some value, okay, between these two gradient of temperature. Okay. So in that way, I have a temperature dependent material from the electrical side also, and I have a temperature dependent material from the thermal side also. Okay, so that completes the information uh, for this conductive material. Okay, so I have structural material, I have uh, thermal material, and I have material which has some information on the electrical side. And for the non-conductive, it is just I have a structural material and I have a thermal material also with conductivity. Okay, so I have some conductivity information, and only this. There is nothing on the electrical side. Okay, so these are two materials what I have. And in terms of property, yeah, it is nothing much. Everything is a solid element. So I just have P solid for the entire thing. So before getting into the thermal part, which is not the complete focus of today's session, otherwise there is a convection case what I have set up. So I can briefly show how the convection case has been set up, but that is on the thermal side. Okay, but here, before getting into the thermal side, I want to go more on the electrical side, how we have defined the loads and boundary condition. So I'm coming to directly on the loadings. Okay, so I have the structural SPC, which I require at a later stage when I want to just run it and get the result for stress and strain. So this is a structural boundary condition. This is nothing new. So I have just constrained some of the locations in all the directions. Okay, so nothing new here. But on the electrical side, yeah. So here there is a difference. So on the electrical side, yeah, though you're seeing from the hypermesh point of view, SPC as thermal here, but these are actually electrical boundary condition. Okay, so why I say that is, yeah, so just see the difference here. So this SPC, if I on, so here I don't have your regular C, which is direction, which we defined. So directly I have some value at D. Okay, so like now from the help document point of view, if you see, so yeah, so this is the component where we define our DOF. But like now, you can see that for a electrical simulation, this field will leave it blank. Okay, so then the solver will understand like this is not the structural boundary condition. Instead, whatever we define in D, that will be treated as electric potential, which is voltage. Okay, so in that way, what is done here is at various locations. Review, yeah. So at various location, I'm setting the voltage to 0. Okay, because for the current to flow, it will flow uh, from the high potential to the low potential. So in that way, it requires this boundary condition. Okay, so either it should have some value or it is set to, like, this is the region from where the current is outflowing. Okay, so in that way, I have set here, here, and these locations. So at all those locations, now voltage is set to 0. Okay, so everywhere it is 0. It is just referring to different set, but otherwise values are 0. Okay, so this is in a way the boundary condition what I have from the electrical side. Okay, so this is a thermal SPC that I'll come to it later, but this is from the electrical point of view, the boundary conditions what you have. And from the current point of view, like yeah, so this is a new keyword, current. So here we are, yeah, so on these locations, so we are loading as a current. Okay, so review is already on, so you're seeing it. Yeah, so there are different values like 0.15. Yeah, so this is something interesting here. So you can see 0.15 positive and 0.22 negative here. So here positive indicates the inflow of the current and negative indicates the outflow of the current. Okay, so in that way, yeah, like here and all these 6 locations, yeah, all these 6 locations, it is inflow. Okay, and I have yeah, these 2 locations which are outflow. So this is the loading what we have, and all the loading are in the same collector. So I can just call that as a loading. Okay. So this is from electrical like boundary condition and setup point of view. So in that way, if you see the model setup uh, in the steps, so first my electrical. So in the electrical, I have got all these SPCs which are called as voltage, and I have the loading which is current. Okay, so that is purely from uh, uh, loading point of view. Okay, and here analysis type I'm taking it as electrical. And now this is where I'm creating a linking where okay. So let me now go to the temperature point of view from the thermal point of view. So from thermal point of view, what all I'm doing is as it is a convection case, what I'm creating. So I'm doing these things in the loads. Yeah, in the SPC where we went earlier. So it requires one, since I'm doing the convection case now, it requires one node in the space where I define the ambient temperature. Okay, so that ambient temperature is, okay, so that ambient temperature, I'm taking some arbitrary, some free node where I'm telling like the ambient temperature is 293. And for the convection, now I have to set up the case for convection where I can create the convection card. And yeah, so I have created on all these boundaries, okay, on all the surface boundaries which I have chosen in my element set, okay, as the faces of these element, and I have created them as the convecting surfaces. Okay, so they are all convecting surfaces for me. And I have to also create a property for the convection. So in that, the main information what I'm giving is like now here, I can say the convection information directly here by setting this F type as 3, where it is a convective coefficient that I'm setting to a value either by this way, or there is also a possibility from the material you can define the convection. Okay, but here I'm going directly with the property. So this convection is set and ambient is set, and from the thermal yeah, loading point of view, this you have already seen how it is. So apart from that, we have a temp D card uh, which we use, like let's say if some node is not having the temperature, then what is mentioned in the temp D, it will be taken as the temperature loading. Okay, so with that, my setup here it is complete for the thermal also. Okay, that is the thermal one. Okay, so I'm calling that SPC what you saw, and yeah, this I'm performing it as a nonlinear heat transfer. So I have NL param card, my regular NL param, but with I'm solving with NINC as 100% loading at once, and yeah, nonlinear heat I'm solving. Okay, and I have my other convection thing set in that. But here the main thing is like now this is a new card, the joule what I mentioned. So here I have to refer the electrical subcase. Okay, so here I'm calling that subcase which is 1. This is the electrical one that I'm calling to link this thermal and electrical. Okay, so that is the linking. And finally on my structural case, I'm just referring because when we solve the thermal case, we only get the thermal output, grid temperature, those output we get, but we don't get stress strain. Okay, so for that we have to solve maybe one empty structural case just with the boundary condition. So to get all the structural output, that's why I have this structural case with just SPC as a boundary as a constraint condition, and I'm just solving it with my output request. And even here also from where it has to get that information, I'm calling the subcase 2, which is my thermal case. Okay, so this is the sequence. So with this, yeah, I have some of the generic output request. So with this, I have output here. Yeah. So first on, so this run, when we run this one, let me go to the folder. So when we run this, we get two H3Ds. Okay. So I have one regular H3D, so which is having result for my heat transfer, and it is also having the result for my structural. Okay, that is this H3D. Whereas the electrical entities are dedicatedly there in a different H3D, which is this one. Okay, electrical H3D. So in that way, okay, maybe first let's see the electrical one. Okay. Yeah. So here, so here from the, yeah, okay, let me choose the sub case. Yeah. So here from the, yeah, from applied current, we know that we have applied current at these location. There were positive and negative values. Yeah, we are just seeing it as a O-load sort of thing. We are seeing it. And the other interesting thing is, let's see the resistivity. Okay, yeah.
Prashant sir,
So
just a moment. Can we like have a poll also in this thing when we time, because we have a hard stop at quarter to. Actually, just to remind you.
okay, yeah, I'm done. I'm almost done. Yeah. Okay. So uh, on the resistivity side, like here you can see we have highest resistivity here. So point to keep in mind is where we have the highest resistivity, there we will have the highest temperature rise also. Okay, so just remember this region. So we have the highest resistivity. In similar lines, the conductivity will be opposite of that. So yeah, you can see it is opposite. So this is some information on the electrical side. Now, if I see the results on the thermal side, okay, so yeah, so I have results here on the thermal grid temperature. Yeah, so these are the grid temperature. Okay, so as you might remember, like we had the highest resistivity here, so we have the highest temperature rise also, and the other region we had temperature information. So finally, on the structural side, yeah, on the structural side, I can see my regular displacement, stress, strain, those for which the loading is from the thermal side. Okay, so these are the information from the structural side. Okay, yeah. So in this short time, of course, overshooting by 4 minutes. So the attempt was to show the setup for the electrical simulation, and further the things which are not shown here is on the contact side. Okay, so it is possible where you'll perform a nonlinear simulation and they will establish the contacts, and from the contacts and from the contact pressure and from the contact clearance, there is a possibility of change in the conductance. So by taking into account of that and performing the same electrical simulation in the downstream. Okay, so those are also possible in the electrical simulation in front. Okay.